Hello everyone, this is Vashishta from Aerobase section. Today I am going to tell about paragliders launch trajectory is universal in aerospace propulsion. So coming to the introduction, paraglider is an young adventure sport consisting in flying lightweight, free-flying, foot-launched glider aircraft with no rigid primary structure. For a physicist, it is truly is a bottomless drawer of fascinating unexplored phenomena, combining a variety of fields covering fluid mechanics, fluid structure interactions, flight mechanics, material science, micrometeorology, and even game theory in the context of understanding exploration and exploitation optima in paragliding competition. So as you can see that paraglides are the most a sport game which is used since the first prototypes. Paraglide wings haven't ceased to evolve, both in terms of performance and security. While most of the research done by paragliding manufacturers has focused on the optimizing wing for steady flight phases, unsteady regimes have only received limited attention. In particular, many questions remain unsolved when it comes to dynamics of stalls or wing collapses, combined with the aircraft's specific pendulum motion. Due to potential limitations of model air experiment, namely the difficult to scale down the stiffness of the material, we decide to perform real scale experiment on the fields with nevertheless showed excellent agreement. So the first reduced scale experiment where it comes with the aim of working in a controlled environment to ensure reproducibility of our results. We start with a reduced scale experiment in which a small paraglider is pulled from its risers along a horizontal 3-meter long guide rail by a wire and pulley system. To minimize friction, the paraglider is fastened to a ring looped around a taut string that serves as the guide. During the launch process, one would like to extinguish two phases. That, during which the cambers filled with air the, to give the aircraft its wing shape, ensuring lift in the second phase where the inflated wing rises from the horizontal to the vertical position. So as you can see, this is the trajectory of an paragliding from 0 to some kind of height. As a reduced scale experiment, the top left caption shows corona photography runs of experiment with respectively 7 newtons and 15 newtons. The time step is between 40 meters. And we can see in this another figure the dimensionless trajectory of trailing edge of a reduced scale glider during launching at constant traction force with x is equal to x dash y is equal to y dash. For different values of traction force denoted by grayscale bullet markers, corresponding trajectories for the real scale air design. UFO glider. Evolution of glider angle, rescaling with the characteristic time scale. As we can see in this figure 2, a display that the dimensionless trajectory of a trailing edge during launching runs with different values of traction force ranging from 5 to 9 to 17 to 8, and its position is tracked manually using image J for image analysis. Note that the third string that is used as a guide rail tends to distort a little under the pulling action of a glider. Strikingly enough, of trajectories fall on top of each other in figure 2a, thereby indicating the independence to the traction force and universality of the launch trajectory. The traction force however, determines the speed at which the paragliders move along the universal trajectory. As shown in the time evolution of its angles, all shall be discussed in section 3. The force therefore sets the characteristic timescale of ascent, with m the wing mass and the length of the glider lines as a function of t. Real scale example. Concerned with the difficulty to downscale all characteristics of a real glider, we decided to confront our results to scale real experiments using 13-meter square flat single surface glider. We were able to record a few launches on calm day at Pude Down. A seasoned test pilot was asked to launch with low and strong traction strength respectively. Unlike laboratory experiment, a slight wind was present here with speed around 7 meter per second measured during each run. As you can see in this diagram, with a real scale experiment, the time step which is on 200 milliseconds, where the pilot, see as you can see here, the pilot is moving from having a trajectory. To account for this, to be able to compare both of configuration, the wind is treated in an additional forward motion of a paraglider at constant speed in a still air environment. As you can see, the trajectories collapse with their residual counterparts, thereby validating the reduced scale methodology. Theoretical model. In this section, we present a simple theoretical model to account for the experimental results. We assume that the rigid glider of a mass m is characterized by its lift and drag coefficient, commonly denoted CL and CD, where alpha is the angle of attack the lift and drag force is applied to center of pressure. As you can see, lift formula it is equal to half rho SC alpha V square E, and the drag is vice versa with the D. With rho, the air density is the platform wing area, and Vm is the norm of a velocity of m in Lab's frame reference. We further assume that the center of pressure is attached to the traction. Schematic supporting the theoretical model. Applying Newton's second law of point m together with the angular momentum theory related to O gives us the following dimension equations. V is equal to cos v minus v plus is equal to rho sv cos c cos alpha plus c sin alpha. With the dimension variabilities t is equal t tends to t by tau v tends to v tau, where we have neglected gravity force as one can see. Fo only appears in the equation through the time scale use non-dimensional time. Therefore, thereby explains the universality of trajectories observed in section 1 and 2 for small-scale gliders. Coming to the discussion, this study revealed a number of other exciting questions such as the optimal folding of the wing for a comfortable launch is in strong wind conditions or the difference between regular and single skin wing during unsteady phases. And the launch phases, particular single surface gliders are known as launch much faster than the regular counterparts. This is often attributed to the fact that they are lighter and thus have less inertial force. But we believe it can be related to the fact that the inflation phase is much faster and argued in section. For regular double skin gliders, the question offers some relief for the chamber air filling and ring phase. In an intricate one, indeed, one expects that the lift coefficient grows possessively as the chambers fill with air, which explains why the wing starts to take off before the glider is fully inflated. This is all my explanation about the trajectory of a paragliding. As for the regular double skin gliders, the question of simultaneity for a chamber air filling and ring phases in an intricate one. Indeed, one expects that the lift coefficient grows progressively as camber fills. Which explains that wing is taken off before glider inflates. Thank you for my thank you for listening.